Medhavy AI, Intelligent Learning Systems. In this deep dive, we unpack why classical physics failed, blackbody, photoelectric, and the photon, Chapter 1 of Quantum Mechanics, Volume 1. Let's get into it.
If you shine a blindingly bright red arc lamp onto a piece of sodium metal, absolutely nothing happens. But the moment you switch to a very dim ultraviolet light, the metal instantly starts sparking, ejecting electrons. Classical physics predicted that light was a continuous wave. If you wait long enough or make the red beam bright enough, the energy should build up and push the electrons free. But that prediction completely fails in the lab. The ultraviolet light works instantly because light arrives as a discrete packet of energy, a single localized particle we call a photon. In this quantum reality, the interaction is strictly one-to-one. A single photon strikes a single electron. There is no pooling of energy and no sharing between adjacent light waves. Because one electron absorbs exactly one photon, we know the light energy isn't washing over the surface continuously. It is delivered strictly in distinct, indivisible collisions. Since light arrives in discrete packets, we need to know exactly how much energy each packet carries. The rule is absolute. A photon's energy is dictated entirely by its frequency, which is the color of the light. The brightness of the beam is irrelevant. We calculate the energy of that single light packet using a specific equation, E equals h nu. Here, E is the energy, nu is the light's frequency, and h is Planck's constant, the universal scaling factor translating frequency directly into energy. The relationship is strictly proportional. If you double the frequency of the light, say by shifting from a lower frequency red to a higher frequency ultraviolet, you exactly double the energy of that individual photon. This means a single flicker of dim blue light, with its higher frequency, hits an individual electron much harder than the intense glare of a massive red spotlight. But the electron doesn't get to keep all that energy. The metal surface holds on to its electrons with a specific grip strength, which we call the work function, represented by the Greek letter phi. You can think of the work function as an inescapable toll the electron must pay to leave the surface. Einstein formalized this interaction in the photoelectric equation. We subtract the metal's grip, phi, from the incoming photon's total energy, h nu. The result on the left side, K max, is the leftover kinetic energy the electron retains once it breaks free. Let's run the numbers. Sodium metal has a work function of 2.28 electron volts. If an incoming ultraviolet photon strikes with 4.13 electron volts of energy, it pays the 2.28 toll, and the electron escapes with exactly 1.85 electron volts of kinetic energy. In the lab, we measure that leftover energy by applying a reverse voltage to the electrons. This is the stopping potential. And to calculate the incoming energy quickly, we use a practical shortcut. Energy equals 1240 divided by the wavelength in nanometers. The math enforces a strict boundary. If an incoming photon's energy is even a fraction of an electron volt below the work function toll, the electron remains trapped. Intensity doesn't matter. A million sub-threshold photons cannot pool their energy to pay a single toll. Let's apply this. You have a piece of sodium metal with a work function of 2.28 electron volts. If you shine ultraviolet light with a wavelength of 300 nanometers onto it, what is the resulting stopping potential? Pause the video here. Use the 1240 shortcut to find the photon energy, subtract the work function, and find the answer. Doing the calculation yourself is how you lock in the concept. Let's check the math. First, use the shortcut. 1240 divided by the 300 nanometer wavelength gives an incoming photon energy of 4.13 electron volts. Subtract the 2.28 electron volt work function, and you get a leftover kinetic energy of 1.85 electron volts. That translates directly to a stopping potential of 1.85 volts. Now, let's test the threshold. What happens if we switch our light source from the ultraviolet laser to a green laser at 546 nanometers? We run the same calculation. 1,240 divided by 546 gives us a photon energy of 2.27 electron volts. That is 1/100th of an electron volt short of the 2.28 work function. Because the incoming photon falls short of the toll, absolutely 0 electrons are emitted. You could blast the sodium with a 10,000-watt green lamp and nothing would happen. The individual photons simply do not have the energy to break the metal's grip. This leads us to the three governing rules of the photoelectric effect. First, frequency controls the energy of the individual photon. Second, intensity controls the quantity of photons arriving, but changes nothing about their individual power. Third, the leftover kinetic energy is entirely dictated by the photon energy minus the work function. By tracking individual light quanta instead of continuous waves, you've calculated the exact phenomenon that broke classical physics. These equations form the mathematical foundation of Albert Einstein's 1905 paper, the exact discovery that earned him the Nobel Prize and proved the universe operates on discrete quantum rules.
That was a Medhavy deep dive. Medhavy, AI-powered intelligent learning systems. On YouTube at Medhavy AI, medhavy.com. Subscribe for the next chapter.